also n, so you have n cubed tests like this. N cubed, so if n is large-ish, n cube's huge, right? So it's a real pain. So testing associativity can be you know, extremely tedious. So when you're testing for something, a subset to be a subgroup, it's an enormous boon. You know, it's a great benefit to know that the parent set is actually a group, because I'm explaining it right now. That allows you to drop testing the associativity of your subgroup or your potential subgroup. Why? Well, so if x, y, and z all belong to your H, okay, your subset that you're testing to see if it's a subgroup, so for all x, y, and z belonging to your subgroup, they also belong to G, right? Because H is just a subset. So any three that belong to your subset belong to your G. But you know, because G is a group, all of these must be associative, right? Or any like this is true. That's true for all A, B, C belonging to G. Okay? Okay, well, just for your ABC, choose only members of H. Okay? But since this is true for all n cubed, and let's say the order of H is I don't know, m. Okay, let's say, so you'll have m cubed possibilities, but all of these possibilities are included in this. Okay? So that allows you, given that you know H is a subset of G and G is a group, that means that any three members of your subset H, they must be associative. So in a sense you can say associativity, that property of your subset H, that gets inherited from G, your parent group. And that's great, because you save yourself this huge effort. So in testing for a subgroup, to prove that a subset is a subgroup, that it's actually a group, you only have to test for these three things. You can skip testing for associativity because you know that just gets inherited from your parent group here. Okay? So let's actually do an example here. In the textbook, it's example 6.3.1, so chapter 6, section 3. Well, no, I'll do a theorem. I'll do this theorem first. Theorem 21. I'll clean the board. Just a minute. Okay, so this is the first, and there are not many, the first theorem of this lecture, and I'll state it here. So it's theorem 21 in the text. So you've got G as a group. I keep saying this. I'm thinking increasingly of buying myself a larger blackboard, so everything that I'm dealing with is dry, so I don't have to worry about the problem when I wipe something out, and I need the wiper to be a bit wet, otherwise it just doesn't seem to work. But if it's wet, then I can't write on it afterwards. So it's a bit of a catch-22 with whiteboards. Another possibility, I suppose, is to buy a higher quality marker pen and perhaps a better whiteboard. So I'm still debating which way I should go. I mean, this is the first lecture maybe of hundreds, right? So teething problems to be expected. Put yourself in the same boat. Okay, so here's theorem 21. And remember, as I said in the previous lecture, Barnard, the first author of this text, he just numbers his theorems starting at the first and just goes right through to the very end of the book. So he ends up with about theorem number 80 or so. Okay, so this is theorem 21, and here it is. So you've got, so you have a group G, right, and you have a subset H, right? So your symbol of a subset. So H is a subset of G. Then H is a subgroup. So H is a subgroup, sub G, I'll just say, is a subgroup of G, if and only if. So it's a two-barreled proof, you know, in two directions. We've done this many times already, so you should be quite familiar with the notion of IFF. If and only if, and then three conditions. In fact, they're these. Look. Now, what are these three conditions? Let xy belongs to H for all x and y belonging to H. Okay, and the next condition, that E belongs to H. E is dry. That's another thing. Chalk does not dry out the way these pens do. Okay, so E belongs to H, and the third one is that for all x belonging to H, x inverse belongs to H. Okay. So now, as usual, with these if, IFF, if and only if type proofs, we'll call this statement, mathematical statement, call that P. We'll call this statement here Q. Call it Q. Okay. Now, as usual, convention is start with the if part of the problem. So P if Q. So P is true if Q is true. So if you have Q, you've got P. So if Q, then P. Right? So if you've got that, prove this. Right? So you start with the right-hand side and you prove the left-hand side. So what do we have to? So we're given this, and we have to prove that H is a subgroup of G. Right? Now the very first thing we need to know is H a subset of G? I mean, if H is something completely wildly different from G, nothing to do, no connection with G, it can't be a subgroup, right? Because it's not even a subset. Okay, so the first thing is we need to know that it's a subset. Well, it is. We're given that. Okay, so H is a subset of G, and we know the binary operator We just get that from G. We're assuming these, well, it's implicit, but in a sense, the binary operator here, remember just XY is a shorthand notation. It's just short, like XY. God, Jesus. I'll take a new one. So XY is just a shorthand for X binary operator Y. Okay? So implicit here with the binary operator, where does that binary operator come from? Well, it comes from G. So this binary operator for H will be inherited from G. It's just the same one. Okay? Alright, so we start with this, and we have to prove this. Now, given the timing, I think I'll stop here.